Earth's rotation is the rotation of the planet Earth around its own axis. The Earth rotates from the west towards east. As viewed from North Star or polestar Polaris, the Earth turns counterclockwise. The North Pole, also known as the Geographic North Pole or Terrestrial North Pole, is the point in the Northern Hemisphere where the Earth's axis of rotation meets its surface. This point is distinct from the Earth's north magnetic pole. The South Pole is the other point where the Earth's axis of rotation intersects its surface. In Antarctica, the Earth rotates once in about 24 hours with respect to the Sun and once every 23 hours, 56 minutes and 4 seconds with respect to the stars. Earth's rotation is slowing slightly with time, thus, a day was shorter in the past. This is due to the tidal effects the Moon has on Earth's rotation. Atomic clocks show that a modern day is longer by about 1.7 milliseconds than a century ago, slowly increasing the rate at which UTC is adjusted by leap seconds. History. Among the ancient Greeks, several of the Pythagorean school believed in the rotation of the Earth rather than the apparent diurnal rotation of the heavens. Perhaps the first was Philolaus, though his system was complicated, including a counter-Earth rotating daily about of central fire. A more conventional picture was that supported by Hycetes, Heraclides and Ecphantus in the 4th century BCE, who assumed that the Earth rotated but did not suggest that the Earth revolved about the Sun. In the 3rd century BCE, Aristarchus of Samos suggested the Sun's central place. However, Aristotle in the 4th century criticized the ideas of Philolaus as being based on theory rather than observation. He established the idea of a sphere of fixed stars that rotated about the Earth. This was accepted by most of those who came after, in particular Claudius Ptolemy, who thought the Earth would be devastated by gales if it rotated. In 499 CE, the Indian astronomer Aryabhata read that the spherical Earth rotates about its axis daily, and that the apparent movement of the stars is a relative motion caused by the rotation of the Earth. He provided the following analogy: just as a man in a boat going in one direction sees the stationary things on the bank as moving in the opposite direction, in the same way to a man at Lanka the fixed stars appear to be going westward. In the 10th century, some Muslim astronomers accepted that the Earth rotates around its axis. According to al-Biruni, Abu Said al-Sijzi invented an astrolabe called al-Juriki based on the idea, believed by some of his contemporaries, that the motion we see is due to the Earth's movement and not to that of the sky. The prevalence of this view is further confirmed by a reference from the 13th century which states, according to the geometers, the Earth is in constant circular motion, and what appears to be the motion of the heavens is actually due to the motion of the Earth and not the stars. Treatises were written to discuss its possibility, either as refutations or expressing doubts about Ptolemy's arguments against it. At the Maragha and Samarkand observatories, the Earth's rotation was discussed by Tusi and Kushji. The arguments and evidence they used resemble those used by Copernicus to support the Earth's motion. In medieval Europe, Thomas Aquinas accepted Aristotle's view, and so, reluctantly, did John Burdin and Nicolaus Mauer in the 14th century. Not until Nicolaus Copernicus in 1543 adopted a heliocentric world system did the Earth's rotation begin to be established. Copernicus pointed out that if the movement of the Earth is violent, then the movement of the stars must be very much more so. He acknowledged the contribution of the Pythagoreans and pointed to examples of relative motion. For Copernicus, this was the first step in establishing the simpler pattern of planets circling a central sun. Tycho Brahe, who produced accurate observations on which Kepler based his laws, used Copernicus's work as the basis of a system assuming a stationary Earth. In 1600, William Gilbert strongly supported the Earth's rotation in his treatise on the Earth's magnetism and thereby influenced many of his contemporaries. Those like Gilbert who did not openly support or reject the motion of the Earth about the Sun are often called semi-Copernicans. A century after Copernicus, Riccioli disputed the model of a rotating Earth due to the lack of then observable eastward deflections in falling bodies. Such deflections would later be called the Coriolis effect. However, the contributions of Kepler, Galileo and Newton gathered support for the theory of the rotation of the Earth. Empirical tests. The Earth's rotation implies that the equator bulges and the poles are flattened. In his Principia, Newton predicted this flattening would occur in the ratio of 1 to 230, and pointed to the 1673 pendulum measurements by Richter as corroboration of the change in gravity. But initial measurements of meridian lengths by Picard and Cassini at the end of the 17th century suggested the opposite. However, measurements by Maupertuis and the French geodetic mission in the 1730s established the flattening, thus confirming both Newton and the Copernican position. In the Earth's rotating frame of reference, a freely moving body follows an apparent path that deviates from the one it would follow in a fixed frame of reference. Because of this Coriolis effect, falling bodies veer slightly eastward from the vertical plumb line below the point of release, and projectiles veer right in the Northern Hemisphere from the direction in which they are shot. The Coriolis effect is mainly observable at a meteorological scale, where it is responsible for the differing rotation direction of cyclones in the northern and southern hemispheres. Hooke, following a 1679 suggestion from Newton, tried unsuccessfully to verify the predicted eastward deviation of a body dropped from a height of 8.2 meters, but definitive results were only obtained later, in the late 18th and early 19th century, by Giovanni Battista Guglielmini in Bologna, Johann Friedrich Benzenberg in Hamburg and Ferdinand Reich in Freiburg. Using taller towers and carefully released weights, a ball dropped from a height of 158.5 meters departed by 27.4 millimeters from the vertical compared with a calculated value of 28.1 millimeters. The most celebrated test of Earth's rotation is the Foucault pendulum, first built by physicist Elie Cousteau Foucault in 1851, which consisted of a lead-filled brass sphere suspended 67 meters from the top of the Panthéon in Paris. Because of the Earth's rotation under the swinging pendulum, the pendulum's plane of oscillation appears to rotate at a rate depending on latitude. At the latitude of Paris, the predicted and observed shift was about 11 degrees clockwise per hour. Foucault pendulums now swing in museums around the world. Rotation period. True solar day. Earth's rotation period relative to the Sun is its true solar day or apparent solar day. It depends on the Earth's orbital motion and is thus affected by changes in the eccentricity and inclination of Earth's orbit. Both vary over thousands of years, so the annual variation of the true solar day also varies. Generally, it is longer than the mean solar day during two periods of the year and shorter during another two. The true solar day tends to be longer near perihelion when the Sun apparently moves along the ecliptic through a greater angle than usual, taking about 10 seconds longer to do so. Conversely, it is about 10 seconds shorter near aphelion. It is about 20 seconds longer near a solstice when the projection of the Sun's apparent movement along the ecliptic onto the celestial equator causes the Sun to move through a greater angle than usual. Conversely, near an equinox the projection onto the equator is shorter by about 20 seconds. Currently, the perihelion and solstice effects combine to lengthen the true solar day near December 22 by 30 mean solar seconds, but the solstice effect is partially cancelled by the aphelion effect near June 19 when it is only 13 seconds longer. The effects of the equinoxes shorten it near March 26 and September 16 by 18 seconds and 21 seconds, respectively. Mean solar day. The average of the true solar day during the course of an entire year is the mean solar day, which contains 86,400 mean solar seconds. Currently, each of these seconds is slightly longer than an SI second because Earth's mean solar day is now slightly longer than it was during the 19th century due to tidal friction. The average length of the mean solar day since the introduction of the leap second in 1972 has been about 0 to 2 milliseconds longer than 86,400 SI seconds. Random fluctuations due to core mantle coupling have an amplitude of about 5 ms. The mean solar second between 1750 and 1892 was chosen in 1895 by Simon Newcomb as the independent unit of time in his tables of the sun. These tables were used to calculate the world's ephemerides between 1900 and 1983, so this second became known as the ephemeris second. In 1967 the SI second was made equal to the ephemeris second. The apparent solar time is a measure of the Earth's rotation, and the difference between it and the mean solar time is known as the equation of time. Stellar and sidereal day. Earth's rotation period relative to the fixed stars, called its stellar day by the International Earth Rotation and Reference System Service, is 86,164.098 903,691 seconds of mean solar time. Earth's rotation period relative to the precessing a moving mean vernal equinox, named sidereal day, is 86,164.090 530,832.88 seconds of mean solar time. Thus the sidereal day is shorter than the stellar day by about 8.4 ms. Both the stellar day and the sidereal day are shorter than the mean solar day by about 3 minutes 56 seconds. The mean solar day in SI seconds is available from the IERS for the period 1623 to 2005 and 1962 to 2005. Recently, the average annual length of the mean solar day in excess of 86,400 SI seconds has varied between 0.25 milliseconds and 1 millisecond, which must be added to both the stellar and sidereal days given in mean solar time above to obtain the lengths in SI seconds. Angular speed. The angular speed of Earth's rotation in inertial space is times 10⁻⁵ radians per SI second. Multiplying by times yields 360.9856 degrees mean solar day, indicating that Earth rotates more than 360 degrees relative to the fixed stars in one solar day. Earth's movement along its nearly circular orbit while it is rotating once around its axis requires that Earth rotate slightly more than once relative to the fixed stars before the mean Sun can pass overhead again, even though it rotates only once relative to the mean Sun. Multiplying the value in radian per second by Earth's equatorial radius of 6,378,137 meters yields an equatorial speed of 465.1 meters per second, 1,674.4 kilometers per hour, or 1,040.4 miles per hour. Some sources state that Earth's equatorial speed is slightly less, or 1,669.8 kilometers per hour. This is obtained by dividing Earth's equatorial circumference by 24 hours. However, the use of only one circumference unwittingly implies only one rotation in inertial space, so the corresponding time unit must be a sidereal hour. This is confirmed by multiplying by the number of sidereal days in one mean solar day, 1.02737,909,350,795, which yields the equatorial speed in mean solar hours given above of 1,674.4 km per hour. The tangential speed of Earth's rotation at a point on Earth can be approximated by multiplying the speed at the equator by the cosine of the latitude. For example, the Kennedy Space Center is located at 28.59 degrees north latitude, which yields a speed of cos 28.59 degrees times 1,674.4 km per hour equals 1,470.23 km per hour. Origin. The Earth's original rotation was a vestige of the original angular momentum of the cloud of dust, rocks, and gas that coalesced to form the solar system. This primordial cloud was composed of hydrogen and helium produced in the Big Bang, as well as heavier elements ejected by supernovas. As this interstellar dust is heterogeneous, any asymmetry during gravitational accretion resulted in the angular momentum of the eventual planet. However, if the giant impact hypothesis for the origin of the Moon is correct, this primordial rotation rate would have been reset by the Theia impact 4.5 billion years ago. Regardless of the speed and tilt of the Earth's rotation before the impact, it would have experienced today some 5 hours long after the impact. Tidal effects would then have slowed this rate to its modern value.